Hello everyone, I'm Erfan, a lead software engineer at DevSH Graphics Programming. Welcome to this talk about porting n4ce's old GDI renderer to Vulkan. We have a lot of ground to cover, but let's first talk about n4ce. n4ce is a survey processing and modeling tool. Survey mapping is an essential process in the development and management of any piece of land, and software such as n4ce have been around since the 1980s, and their capabilities have evolved to take measurements from all survey instruments such as total stations, GNSS, and LiDAR point clouds. And so the size of the survey kept on getting larger and larger, reaching millions of curves and points. While n4ce kept up with the state-of-the-art feature extraction using machine learning on CUDA, the 2D rendering retained the legacy implementation in the Windows graphics device interface. Windows GDI is basically an old immediate mode renderer for Windows. You can draw lines by moving markers around. We noticed two visual deficiencies that we wanted to fix. Curves had to be polygonized before feeding to GDI. This results in considerable error with the original definition of a curve, and we have no smoothness. And the biggest problem is that you have to have a lot of straight lines to reasonably approximate the original curve. And there is aliasing. Did I mention this survey takes 22 seconds to render a single frame with GDI? It contains more than 500,000 lines and curves combined. Of course, other than GDI, there were still a lot of performance pitfalls such as large temporary memory allocations and not caching polygonized data. So we want the new renderer to be faster, obviously, for our heavy scenes to be interactive. We want it to have higher quality with anti-aliasing, transparency, and smoother curves. And we want it to have less error, meaning less difference from actual shape. n4ce is a 20-year-old code base coupled with immediate mode rendering. There is going to be limitations on our rendering architecture. n4ce does other things with the GPU, so available VRAM is not enough for the data we need access to on the GPU. There should be an overflow mechanism. More importantly, n4ce has an implicit scene graph with recursive function calls, and we cannot change this and re-engineer the entire application. We want to traverse the scene only once, but there are too many draws to push into temporary buffer and sort by pipeline. We can't reorder draws because transparency order depends on the scene graph traversal. So the best solution we came up with is to have one graphics pipeline to render every object. This choice of having one pipeline also makes GPU-driven rendering and calling achievable because we no longer have an unknown number of pipeline switches. And we're targeting Windows desktop with GPU supporting following Vulkan features: shader clip distance for customized clipping, a scale-up block layout for HLSC++ struct compatibility, shader float 64 because we need to work with double precision coordinates in CAD, but this feature is unfortunately not available on Intel GPUs, so we need to emulate when this feature is not present. Buffer device address, so we can have a single buffer to store data with multiple types. It can be emulated using different descriptors on the same binding, so it's optional. Fragment shader interlock for a transparency algorithm explained later in this talk. Here is what we were able to achieve so far, quality-wise. As you can see, the aliasing is gone. And for performance, here is a comparison for two simple surveys with a few thousands of lines and curves. Orange is before, green is after, timing is in milliseconds to render a single frame, so the loss is better. Okay, I need to bring it to logarithmic scale. What takes n4ce almost a second only takes 11 milliseconds on GPU with Nabla. Both include the time spent on the CPU to construct the geometries from scene data without caching them. Before getting into how a rendering pipeline is structured, we should first define what's the problem we're trying to solve. What kinds of objects are we trying to render? We have straight lines and elliptical arcs. Okay. And then we have some complex curve. They are a blend of two parabola or two elliptical curves along a chord. And we have offsets to each of those curves. Offset curve is the original curve added to its normal. So it's not a simple transformation. It changes the whole mathematical definition. So it's an added complexity for each new curve type we introduce. It doesn't end there. Each of those curves need custom stylization. they need the dash pattern applied to them, also known as simple patterns. We cannot use hardware line primitives with GLSI 16-bit simple patterns for several reasons. The styles are vectorized and have inferior resolution. Lines have custom end caps. Line width can be in bold space. So as you can see in the image, you can zoom into it. The left one has a mitre ring. The right one is connected with circles. So in order to achieve that, without breaking our curves into multiple small geometries, we need to compute arc length and its inverse for our curves, because we need a mapping between the position on the curve and position on the pattern. Remember calculus? Let's look at our blended elliptical curves again. Here is their general equation, which we blend with an interpolation function along the chord. And here is their arc length. I only use this example because the equation would fit in the screen, but it is enough to make the point that these are complex curves we are dealing with. We have to go through this process for every new curve type introduced, and the associated offset curve counts as a new type by itself. Now we're ready to begin walking throughout the ranging pipeline. We start by transforming our pre-computed curve data to normalized device coordinates and clip them. Then we generate proxy geometry, which tightly bounds our curves, and we feed them to Fragment Shader to render the curves. There is also a full-screen alpha resolve path we will get into when we get to explaining transparency, and finally we submit and incrementally present everything. Of course, there is an overflow mechanism because sometimes none of the pre-computed object data can fit into VRAM, so we will submit and start processing the next chunk. If you're curious, take a look at our Vulkanised 2023 talk, keeping your staging buffer fixed size. But let's ignore that for simplicity. Let's focus on the fragment processing part of the pipeline. Firstly, we want to render our curves and apply styling in the fragment shader, which essentially reduces the cycle spent by the CPU on serial geometry generation and reduces the staging buffer bandwidth. And also, we want to do anti-aliasing, but supersampling is expensive. We're doing most of the rendering work in fragment shader. MSAA is useless without actual geometry, since it's for geometric anti-aliasing and not interior. And alpha to coverage useless here too. It's used for screen door transparency or for anti-aliasing alpha tests, such as in grass rendering in games, as you can see in the picture. But remember, we have one graphics pipeline, and we have blending always enabled for that pipeline because of transparency. So let's compute the coverage analytically and set the pixels alpha. We decided to do that using sign distance fields to render our curves and lines. STFs are signed because negative is the inside of a shape and positive outside, and they tell you the distance to the boundary. Field because it's defined in every point in space, 2D or 3D. And STFs allow for a good approximation of coverage. We reduce pixel coverage from STF value using smooth step because it has nice properties. But computing STFs is expensive, as it requires finding the local minimum of the function that tells you the distance to the curve from the query point. And basic calculus tells us that to find local minimum of a function, we need to differentiate it. The more complex the curve, the more complex the root finding on function d prime. That's why we want to tightly bound the curve to reduce the number of fragment shader invocations that do not contribute to anything and redundantly perform this STF computation. Pre-computed bounding geometries won't work. Imagine you zoom in on a small part of this parabola that's off the curve. Now it covers the entire screen, and the STF is evaluated for every pixel on the screen. Even oriented bounding boxes have a poor overdraw ratio. That's why we decided to bound our curves with custom bounds, like the image you see on the screen. But it's not as simple as you think. It requires finding extreme points of a curve. So far, we've seen that for each type, we have different equations. For STF, proxy geometry generation, and arc lengths, which require individual analysis of singularities where precision breaks down. Here is a photo album of what we were dealing with regarding precision issues. Keep in mind that we want to avoid doubles in fragment shader at all costs, because GL position is a still 32-bit floating point. 64-bit floating point is half rate compared to 32 or worse on most GPUs. And it also unfortunately has a double type but doesn't provide important functions such as the square root length we need and implicitly cast to 32-bit. So for each curve type, we have to generate a tight-bound polygonal mesh, calculate the STF function, compute arc length, which requires finding the derivative of the curve, compute inverse arc length. There is even more we will get into, and all of the above needs to go through error analysis, tests, and be made numerically stable. That's why we chose to turn any complex curve into piecewise BZAs. This gives us huge benefits. The properties and the precision of their computations are better studied as there are thousands of articles on BZAs. Numerical stability is now achievable much easier, and having a single curve type is heaven for maintainability and results in a faster development time in the long run. We chose to use quadratic Beziers, even though cubic Beziers have a higher degree of freedom and can approximate a curve more precisely, but at a higher cost. The STF of a quadratic is more numerically stable than for cubic. Arc lengths of a quadratic can be computed analytically, and this makes the inversion much faster. Intersection of two quadratic Beziers can be solved analytically, but cubics require numerical methods. Our benchmarks also showed the quadratic STF is 4 times faster to evaluate compared to a cubic. This is our pipeline, which turns any C1 differentiable parametric curve into a bunch of BZAs until a certain accuracy is met. And this makes us future-proof against new types of curves. This is just a fancy graph for a simple process, which means subdivide until you don't need to anymore. The most important part is that we find the subdivision point by importance sampling the arc lengths, which really means with each subdivision we break the curve into 2 parts with equal arc lengths. We also thought about importance sampling other functions such as curvature, but those didn't work well. In this case, 4 quadratic BZAs result in a higher accuracy than 1024 straight lines. And we can see we have almost a 45-degree slope in logarithmic scale, which means with each subdivision level, we cut down the error by a factor of 2. Now let's get into more details on how everything is built on top of Nabla, our open source framework for working with Vulkan. Nabla has no global state. It can run side by side other APIs, it can run side by side OpenGL, DirectX, Vulkan, and it can even interrupt resources with them. In Nabla, functions can be called from any thread, mostly in external synchronization, and there is no global window, so you can spawn windows, surfaces, and swap chain whenever you like. All of this is very useful for porting in situ, where we can run them side by side even with their difference and notice any visual bugs during the development phase. A standout feature for us in Nabla is sharing code with HLS and C++. Helps a lot with maintaining a large project, as there are a lot of similarities between C++ CPU code and the shaders on the GPU. As an example, we need to calculate the arc lengths of a Bezier, both in fragment shader for styling and in the subdivision pipeline for importance sampling subdivision points. One uses doubles, one uses floats, one is a pre-process step on CPU, one is runtime in the fragment shader. Single source HLS C++ also allows us to flip-flop between CPU and GPU for calling or proxy geometry generation at moment's notice. As a bonus, you can debug and prototype shaders on the CPU without expending effort to think about setting up the scripters and pipelines. Because of the alpha blending, we need the output of the calling stage to maintain the ordering of the input. This is easy for a serial CPU implementation, but it is tricky on the GPU. A parallel prefix sum, also known as a scan, performed on a global array, is an indispensable building block of a GPU-ready sort or compaction, and Nabla helps with that by providing global compute and worker reusable scan and sort primitives.
So this is now my part of the presentation, where I'm going to talk to you about a new algorithm, never before seen. So transparency and anti-aliasing. Alpha depends on the coverage and overall transparency, right? They get multiplied together. The proxy geometries are conservative, so they overlap. Now, the Beziers for the same group ID should not overblend on their intersections. This could be solved analytically by careful mitering where they touch. However, we also have to fall back to bounding boxes when the curvature gets so great that curvature times the line width is greater than 4. And the reason is that it's really hard to find out where to put the offset curve, because the offset curve kind of overlaps itself. You can kind of see the curve at the bottom. It's falling back to the OBB method because it has a sharp kink in it. And the solution is to invent a new, never seen before algorithm for transparency. And it's called the frame buffer space constructive solid geometry with sign distance field. So we begun with a what if idea of having drawing proxy geometry twice, right? So let's say we use a stencil buffer, and we accumulate the alpha values in the stencil buffer, and then for that we would obviously need programmable stencil export and a late stencil test, and then we turn the color right on, and the stencil pass to greater than 0 and clear, and then we'd use the stencil buffer to modulate the alpha, and then the first pixel drawn results the color, the rest are dropped. But you can't actually do that because, well, you can't tap the stencil buffer you've currently got bound, right? And also, didn't we say we've got one pipeline and draw call for everything? I mean, it's kind of difficult to change all the state in between. But what if we actually did have a programmable stencil buffer, like programmable blending? Enter fragment shader interlock. Fragment shader interlock allows for a single critical section in the fragment shader, which is entered into with regards to rasterization order, allowing synchronized access to any resource and can be used to implement rasterizer ordered views. Programmable blending of non-hardware blendable formats like shared exponent. Complex per pixel data structures which need in-order atomic modifications, or single pass order independent transparency, such as multiple layer alpha blending. Now, MLab can be implemented with spin lock, that's not UB, but it will be temporarily unstable, it will flicker because the pixels are not being added in the same order. Only one desktop vendor doesn't implement it, despite the ability to do so. And it has open source drivers which do implement it. That's okay. We'll just show a buy a real GPU pop-up with an Amazon affiliate link. Extension seems not compatible with dynamic rendering. I'm not sure that's true. We use unrender patterns anyway, because the spec says something about subpasses and dynamic rendering doesn't have subpasses. So maybe I'll open a spec issue about that. So why is fragment shader interlock much better than other extensions? Well, for this particular case. So currently, all other extensions, they allow shader access to a bound attachment, right? And the memory that you can access is assigned to a pixel. It's usually an attachment. And you can have only read-only access. And if you have like a data structure in those pixels, like let's say you've got 4 attachments, then if you want to modify something, like with MLab, only the modifications after, in the opacities of buckets after the current fragment depth, result in modifications. And containers in general, heaps, trees, linked lists, you need to actually make the modification on the container and then export the whole thing as all 4 pixels or 8 pixels or however many you've got attached. And the rasterization order attachment access does not work with, works with render passes, not with dynamic rendering, and shaded tile image works only with dynamic rendering. So, rasterize all the views is really something else. So our new algorithm. So we can actually achieve the original algorithm by drawing the geometry once. So if the current coverage is is 0, then discard, else enter the critical section. You read the pixel's previous coverage and object ID from image S, which is our programmable stencil buffer that also has object IDs in there. If either object ID changed or cover increased, then overwrite the entry in S, but keep the old one as a temporary in the shader. You exit the critical section, and then if the object ID changed, so the new one is different than the old one, so you've got like an overlap. You take the RGBA color from the style associated with the previous object, which was there, and you multiply the alpha from the style with the previous coverage, which is the old value from S, and you blend it to the output. Now, obviously, the previous triangle cleans up after the previous pixels. So at the end, you need one final full screen triangle, which has alpha 0 and object ID invalid, and it resolves this stencil, programmable stencil completely, and clears it so it's ready for the next kind of full frame draw. So this was loosely inspired by like a never published invention that I made to the Forge a really long time ago, and it was to draw SDF shadow volumes with instancing using the really old deferred stencil live volumes optimization. And what you do is I would make sure that the far face draws first and then the near face. And you do the usual thing where the far face increments the stencil upon the stencil pass and the depth fail and doesn't do anything. And the near face decrements the stencil upon the depth pass and the stencil pass, and then does the work in the pixel shader. So it's like a stencil shadow, but then within that, you run a pixel shader to kind of refine the shadow to do SDF shadows. And it all runs because you'd have a special vertex shader that would actually spin like a cube around. So you'd make sure that the triangles that are in front would get drawn before, sorry, the triangles that are in the back get drawn before the triangles in the front. And it's a total abuse of Vulkan implicit rasterization order guarantees. And I could just draw, instance to thousands of these instances and not have to change anything, pipeline state, nothing. So if you have similar problems, mail us. Questions?
Yeah, thank you for the talk. Did you consider using tessellation shaders now that you were doing Bezier curves instead of the SDF?
Not really, because you're not really solving the problem. You're kind of kicking the bucket down the line. So the problem was that the CPU was tessellating, and now you've kicked the bucket down the line, and now the GPU is tessellating. And I'm still not able to get pixel perfect, whereas with this, you can get pixel perfect.
Do we have any other questions?
Since you mentioned that your workflow is a survey application, do you have any use cases where you have to generate a PDF out of this, or like
it has been asked about. So one of the ideas that, so there's already like a backend which generates PDFs, and there's kind of no reason to replace that. But there was an idea to basically hook up. Let me just have a look. To hook up like transform feedback or just output to an SSBO just before the fragment processing stage. Yeah, but it's not something we're currently working on. Okay, so I'll just give over the podium.